NoSQL focuses upon performance over strong consistency. NewSQL focuses upon strong consistency at the cost of performance, which is right for your business. Without any further ado, I have the pleasure of introducing to you our speaker today. Avishai Ish Shalom, ScyllaDB's developer evangelist. Avishai will take you through the differences and provide a comparison of the benefits of each of these architectures. Take it away, Avishai.
Thank you, Peter. So welcome everyone to the webinar. And I'm going to start by doing a quick run through the history of databases. Don't worry, it's going to be really quick. So in the 70s, we started seeing the beginning of database systems, which originally ran on mainframes. And this is also when the relational model was created. And then shortly after that, in 78, we saw the first SQL database, that was Oracle, and shortly after DB2 from IBM. And in the 80s, SQL and relational databases in general became the de facto standard of the database world. In the 90s, we started seeing open source SQL databases like MySQL and Postgre. And also, this is when we started seeing computer networks. So this is also when we started getting features like replication, external caching, and that kind of stuff. And at the turn of the century, something very interesting happened. We got the internet. And then we started seeing much bigger scale than ever before, much bigger data sets, much higher throughput. And relational databases, which were doing an amazing job up until then, they became limited somewhat. And this is when we started seeing a new generation of databases. So NoSQL databases started popping up from Google, from Amazon, from different companies. And also open source databases. So Cassandra, for example, was published in 2008 based on a project from Facebook, which was based on the Bigtable paper and Dynamo paper from Amazon. And in the following decade, this is when we started seeing a massive shift to the cloud, to commodity hardware, to commodity computers, and also much more databases, much more data sets, so like an explosion of data. So this is also when we started seeing a new generation of databases. So the second generation of NoSQL, things like ScyllaDB, and also a new generation of relational databases, NewSQL, which is what we're going to be talking about today. So first of all, let's start with what is NoSQL. And the problem with NoSQL is that it's kind of an umbrella term. It's everything that's not SQL. So that covers a lot of different databases. Some of them are general purpose, which is what we're going to focus on today. And some of them are special purpose, which we're not going to discuss today. Things like graph databases, metrics databases, search engines, and so on, so on, so on. And when we're talking about general purpose databases, we can roughly put them on a spectrum of simplicity to power. So I'm talking about the data model here. So simple data model, which also allows for simpler architecture, sometimes more performance. This is the extreme side of it would be key value stores like Aerospike. And then the other side of the spectrum, you have things that have more power in terms of data model and also control over data locality. So Widerows, this is the model Scylla uses, DynamoDB and Cassandra, and gives you more power. So it's somewhat less simple, but not as complex as relational databases. And in between, you've got document stores, which have kind of a compromise between those ends of the spectrum. And of course, this is just a rough division. There's also more and more dimensions we could discuss, but in terms of rough division, this is I think gives you a good idea. So why NoSQL? The problem with traditional databases and relational databases in general is that they had a lot of scaling limitation. And this means higher cost for running them, of course, dealing with scalability and performance problems, and also operational and usage simplicity. And with that comes a lot of problems with predictability, both in terms of performance and also in terms of what happens when you have a failure. So those are the main reasons why we started seeing NoSQL at the turn of the century. So when it comes to NewSQL, on the other hand, this is like a totally different family that's somewhat opposed to NoSQL. And it's a new generation of relational databases, but they're distributed. So originally, relational databases were running on monolithic servers. Remember, they're descended from mainframes. So now we have distributed relational databases that support SQL. And of course, you have analytics databases, but today we're going to discuss mostly transactional databases for online OTP, basically. So those databases offer distributed transactions and, of course, ACID guarantees. This is like the big promise of NewSQL. So why NewSQL? First reason is compatibility. It's a familiar model. Everyone's been using relational models for a very long time. So sometimes it's wire compatible with old relational databases. So it's very easy to transition to NewSQL from, let's say, Postgre or MySQL. They also have better scalability than traditional relational databases. And of course, they offer SQL, which is a rich and powerful query language. So you can't discuss relational databases versus NoSQL database without discussing data modeling, because this is a very big part of the difference between NoSQL and SQL databases. So I want to talk a little bit about data modeling, specifically the relational model. So the relational model originally comes from relational algebra, which is a computer science theory, and SQL is based on that. But it has some deviations. It's not exactly the same as the relational model. For example, the relational model does not allow for nulls, where SQL does. But other than those slight deviations, it's roughly the same. So in the relational model, you have tables, which are relations between columns or attributes, as are called in relational algebra, or tuples, and those tables relate to each other using foreign keys. So you have basically keys that connect one table to another using IDs. And you're not allowed to have duplicate tuples. This is part of the consistency guarantees of the database, and no missing values. Of course, as I mentioned, SQL does allow you to deviate from this to some degree. But the idea is that you have many primitive tables and you join data on read. And this is why we have something called normalization. This is a big part of relational algebra. You basically normalize the data such that every table has unique tuples that don't have any duplicate values. That's the general idea. So it looks kind of like this. Let's say that you have a data set that is employees of companies, and you have some data about the company as well. So you break it down into two tables, one table for the companies. So that one doesn't have any repeating data. And also the employees table doesn't have any repeating data because every employee is different from each other. And if you put the company name, for example, with the employee, then you would have duplicate values for the company name column. So you move all of the company attributes to the table of the companies, and you have the foreign key connecting the employees table with the companies table. And then if you look at the query that I've put here, you basically join on company ID, which is a foreign key, and you reassemble the data to the shape that you want, and this is how you get the data that you want from the database. So you basically, on the fly, you join the data, and this is how you get the proper shape with the entire data of the company. So by contrast, the denormalized model, which is what most NoSQL databases use, is like the complete opposite of this. Instead of breaking down the data into different parts, you have a single item with all the data about the company, with list of employees and everything, and you can have duplicate values in there, and there's like minimal constraints over the structure and the contents of that data item. So this means that, of course, you might have, you might use more storage, you might have, some anomalies because you're not actually enforcing any constraints, but it also means that you're doing minimal shaping of the data. So when you query data from the database, the query is very, very simple. So for example, if you do a get query, all you need to do is give, the name of the table and the ID of the item that you want, and that's it. You don't need to provide any information about what shape you want, how to join it, and that kind of stuff. The query is very simple, also very simple to service. But of course, no joins means no joins. So if you want, for some reason, to join it with something else, then you can't. So comparing the different models, in one model, the normalized model, you do data shaping on the fly at read time. And in the denormalized model, you basically pre-shape the data. You do it at the right time, you write that data already in the shape that you want to query it. And this is how you query it. You query it in the shape that you want. But this also means that if you have multiple types of queries, you have to write it multiple times. So it means that, of course, you need more storage because you need to store it multiple times. Also means that you don't have constraints in the normalized model, whereas in the normalized model, you have constraints which are enforced on write time on the fly. And of course, in the normalized model, because you're writing to multiple tables, you have to lock the tables so that the constraints of the database are preserved when you're writing to multiple items at once. This means that structurally, databases that are relational have higher complexity than databases that are non-relational and use the denormalized model, because actually the complexity is on the application side and not on the database side. So that's like the rough difference between the two models. Which brings me to talk about ACID, which is an acronym that gets thrown a lot when we're talking about relational databases and databases in general. So what does ACID mean? ACID is an acronym for atomicity, consistency, isolation, and durability. And this is one of the most misunderstood concepts in the database world today, because it often doesn't actually provide what people think it does. So atomicity means no intermediate states. The main concept of ACID is transactions, and transactions are a block of related statements, and they have to be executed atomically, meaning that they either execute completely and they are committed, or they abort and they roll back. And this means that you either see the data that the transaction written or you don't, and that's atomicity basically. Consistency means that the data constraints are preserved, and this is like the guarantees of the database itself. So if you are guaranteed to have foreign keys, triggers, cascading updates, stuff like that, all of them have to be done by the time the transaction is committed. And this is, of course, different from isolation. Isolation means that if you have concurrent transactions, which is the point of the database, if you don't have concurrency, then this is not really a problem, and you probably don't actually need a database. So you are guaranteed to have isolation, meaning that the transactions do not impact each other. And usually when we talk about isolation, people think about serializability, which is a model that basically said that the database provides something that is equivalent to a serial execution of the queries, meaning that they don't interact at all. But the problem with serializability is that, one, it's very, very expensive in terms of performance, which is why most databases don't actually guarantee serializability. For example, Oracle, instead of serializability, give you something called snapshot isolation, which is not exactly the same thing. We're going to talk about that in a bit. And also that the database is allowed to rearrange transactions as it sees fit. So this is something that a lot of people are unaware of. It's not necessarily a problem, because if you're doing all of the data mutation logic inside of transaction, then it should be fine, at least in theory. But if for some reason you're not doing that, then you might have a problem. And finally, you have durability, which is a guarantee that data that has been committed will still be there even if you have some kind of system fault. So crashes, hardware faults, and so on, so on, so on. So ACID is mostly about concurrency and mutability. If you have immutable data, then of course ACID is not really interesting to you. And if you don't have concurrency, then again, ACID is not really interesting to you. Note that concurrency is also on single server. And actually this model originates from single servers and predates distributed systems. So we've been dealing with concurrent execution for a very, very long time, actually. And this model has been designed for monolithic databases. So this is why it makes promises that are very, very hard to keep for distributed systems. Now, this is a transactional model. Again, as I mentioned, the main, let's say, player here is transactions. So if you're not using transactions, or if you're using a single item or single statement transactions, then ACID is probably not that interesting to you. And the final thing that you have to understand about ACID is that ACID is a database-centric programming model. So as I've mentioned, to get the benefits of ACID, you have to do all your data mutations inside of a transaction. So let's say that you read a value in one transaction, then you commit that transaction and you do something with that value, and then you write it in a different transaction. The database has no way of knowing that there's data dependency between those two transactions, and then you can actually break the constraints of your database, and all kind of weird things can happen. So this means that you have to put all of the data logic of your program in SQL, which means usually stored procedure and stuff like that. And it means that your application is kind of broken in half. Parts of the logic of the application are going to be in SQL, and parts of it are going to be in Java or whatever programming language you use, which a lot of developers didn't like. And this is a quote from the author of the Ruby on Rails, one of the famous web frameworks. So no, Mr. Database, you cannot have my business logic. Your procedural ambitions will bear no fruit, and you'll have to pry that logic from my dead cold object-oriented hand. And so obviously he doesn't like giving control to SQL. So I guess it's a matter of preference, but this is also sometimes a problem when you're debugging stuff and you're trying to understand what your program is doing. So let's talk about the bad stuff in ACID, because ACID is good and it's a good program model that provides a lot of stuff, but the problem with it is that it's not defined well and it's not well understood. So what do I mean by that? So as I've mentioned, serializable is just one of the levels of isolation provided by the ANSI SQL standard. And the other isolation levels, meaning read uncommitted, read committed, and repeatable reads, have what we call phenomena or anomalies, which means that weird things can happen. A lot of developers don't actually understand like what phenomena can happen, when can it happen, and when to use what isolation level. And if that's not bad enough, most of the databases out there actually use very low isolation levels. For example, Postgre by default uses read committed, and MySQL uses repeatable reads by default, for example. And if that's not bad enough, some of the vendors of databases, and I've mentioned Oracle before, but they're not the only ones, have implementations which are different from the ANSI SQL standard. So actually, in practice, there are like 8 different isolation levels out there, with each with its own anomalies and stuff like that, which leads to, for example, exploits. So there's a research called AcidRain, which demonstrated how you can take a coupon and by doing malicious concurrent executions of a web transaction, you can actually cache in that coupon multiple times by exploiting the reduced isolation of a database. Another problem with ACID is that, as I've mentioned, you have to do all of your logic inside a transaction boundary, which means that if you're using cache or read replicas, then you're breaking the ACID model and you can't actually use it. So that's a problem for scaling, but also for a lot of systems that need caching for various reasons, performance or something like that. And actually, in a lot of companies where I worked and consulted, I've actually seen that they unknowingly broke the ACID guarantees that they wanted. And it also means that the application itself has to be transactional in the sense that it does everything within the transaction boundary, but also sometimes propagate it all the way to the user. So remember, users make decisions based on the data they see. So this means data dependencies. Sometimes you have webhooks and so on. So often you hold a transaction open while doing something else, which has grave performance implications for the database. So when we're talking about distributed systems, one of the major theorems that people talk about when it comes to distributed systems is the CAP theorem and also the PAC-ELK theorem. And what the CAP theorem basically says is that there's a trade-off between availability and consistency. CAP stands for consistency, availability, and partition tolerance, and states that you have to choose 2. So first thing is that you can't actually forego partition tolerance. If you forego partition tolerance, it's not a distributed database and it's not really usable, so that's not interesting. So you have to choose actually between availability and consistency, so either CP or AP. This is the trade-off, basically. And this trade-off has to be done when there's a partition. When everything is normal, then you don't have to choose between consistency and availability, but you do have to choose between latency and consistency. This is what the PAC-ELK theorem says, and it's basically an extension of CAP. And it means that even in under normal operating conditions, there's a penalty for having greater consistency, and that means performance and sometimes timeout, which is basically an outage. So the thing to remember is that it's not a dichotomy. So a lot of people try to classify databases in terms of the CAP theorem and say, okay, this database is consistent, this database is available, but the CAP theorem was actually designed to make people think about trade-offs, and usually per transaction trade-offs. So for example, Scylla allows you to have tunable consistency, so you can make that trade-off per transaction. That's a lot more interesting and a lot more useful for applications. Now, the important thing to understand when we talk about the CAP theorem and ACID is that CAP consistency, through very, very poor naming, means something completely different from ACID consistency. So remember that ACID consistency is actually, guarantees that the data and preservation of the foreign keys and the other guarantees the database provides in terms of its data model. So that's completely unrelated to CAP. What CAP consistency means is that all replicas show you the same value, all non-failing replicas show you the same value. So that's something completely different. And actually, if you want to talk in terms of ACID, then this would be something called linearizability, and it's actually equivalent to some isolation level of ACID. And the CAP talks about single item and single statement. So it's not talking about transactions. It's not talking about multi-items at all. So actually, it's like completely orthogonal to ACID. And the only way to like reconcile those two theories with each other is if you have the entire ACID database inside of a single item, which means like global lock. And this is called strict serializability. And it's impossible to provide in highly available fashion. And also like the performance of it is like horrible. So no one does this in practice. So what Eric Boyle, the guy who originally proposed this, the CAP, this was back then conjecture, not even theorem when he proposed it, he actually suggested something that's called harvest yield model, which is a better way to handle those trade-offs. And the idea was that harvest is the percentage of data that you read or wrote, and yield is the probability of completing a transaction. And then you can tune both of those. You can trade harvest for yield and vice versa. And that's the basic reality of all distributed systems, that you have to make this kind of trade-off. So we're going to stop for a poll now and ask you, what is more important to you, availability or consistency?
Great. And while that poll question is up, we had a question from Franklin John. He was asking, ACID combined with optimistic locking using version numbers, isn't it relevant even in distributed trends?
So it is very relevant, and there's actually a lot of people using it. But if you're doing, so ACID is a pessimistic model. It's trying to manage concurrency inside the database. And if you're using optimistic locking, then basically you're moving the management of concurrency from the database to the application, which is sometimes a wise thing to do, especially if you have to hold transactions open for a very long time. Then maybe doing optimistic locking is better. And actually, this is something that we've done in a couple of places. But if you're doing that, then you might as well use NoSQL, which also offer you the ability to do that as well. Unless, of course, you need transactions and you want to combine the two. So yes, this is something that people do.
Great. Thanks for that question, and thanks for your poll answers. We're going to move on then.
Oh, one sec. So this brings me to talk about distributed ACID. How do you build ACID on top of distributed systems? So the problem with distributed ACID is that at least for the high isolation levels, you can't actually make that highly available. Highly available is also something that's very nuanced. Because, for example, in the CAP theorem, when you say highly available, it means all nodes must provide a valid answer. And sometimes, for a lot of people, highly available means that, at least one node survives. It doesn't necessarily mean that you need all the servers. So there's a nuance there. But in general terms, ACID cannot be available, and sometimes to the degree that even a single failing server prevents you from completing transactions. This is one of the problems with, for example, two-phase commit. This is true for the higher isolation levels. Actually, read uncommitted and read committed can be provided in highly available fashion, but this is not something that's actually being implemented in the field currently. And also, those isolation levels are not very interesting because of the anomalies that they have. So remember, CAP doesn't actually apply to transactions, and this is why there's a concept of highly available transactions, which focuses on giving you ACID-like transactions in a highly available fashion, at least for with committed. This is mostly academic stuff. Currently, there's no widespread implementation of this. That's kind of unfortunate, but it's still very interesting read, and also explains the differences between ACID and CAP and how they interplay. Anyway, ACID implies distributed locking. You can minimize it to some degree. So there's some algorithms that people use, some really fancy stuff like Kelvin and other stuff that allows you to minimize the amount of time that you lock the database. But currently, we can't do it without some kind of locking. And this means that there are, of course, performance ramifications, which means that you have lower scalability and higher latency. The good news is that most of the NoSQL databases can provide some equivalent of those isolation levels, not in the ACID term of transactions, but they do provide some things like building blocks you can build on. So this is part of the reason why NoSQL databases are useful. So the major difference in terms of how you view NoSQL and NewSQL is that NoSQL is all about the dynamics of how you query and store data, whereas NewSQL is all about semantics. And I'm going to talk about what it means in a second, but when I think about NoSQL databases, special databases like Scylla, I think of them as part of like a building block, the central building block for data architecture. But a lot of the logic and a lot of the semantics is built on top using other things like by connecting to other things like Kafka and of course in your application. Whereas NewSQL relational databases, they are like a holistic system that actually enforces you to do all of the semantics inside of the system with SQL. So that's like a way to think about this. So what is semantics? Semantics is the what data you want, what shape should it have, what is the schema, how's it stored, that kind of stuff. And the focus is on data integrity and query power, whereas dynamics is basically the how are queries executed, where is the data located, how is it stored, that kind of stuff. So the focus is on performance and scale and not so much on query power and data integrity. This is left to the application. And when I'm talking about scaling semantics, again, it's very different. So NewSQL basically has semantics that relate to the data itself. So not basically abstracts over scale and location. So no real semantics for things like how many replicas you want and how many replicas you want to query. So you can't actually do yield and harvest in a useful way in NewSQL. And also there's a problem where because you have to do a lot of joins and sharding don't interplay very well, so that's of course a problem. And on the flip side, NoSQL gives you explicit control over yield and harvest. This is in our database, at least in Scylla, it's tunable consistency. So an example of this semantics would be in CQL just saying consistency 1, and then you can say I want to read from this query, I want to read from 1 replica. So that's an example of how you can tune this. And it's also partition and shard friendly by design because you're not hiding the fact that there are partitions and shards. And this all gives you the ability to do a very fine-grained tuning of eventual consistency and data consistency in general and availability. When it comes to query semantics, of course, then NewSQL, it's all about power. So you get ad hoc queries for practically everything that you want, and you can mix reads and writes in the same transactions. And you basically let the database worry about how to execute the query, no matter how complicated it is. And remember that SQL queries can be arbitrarily complicated because SQL is still incomplete. And this means that the performance is, of course, unpredictable. It's very hard to do. You can give databases some performance hints to help them to execute the queries in a more efficient way, but it's limited. The semantics for performance hints is very limited. NoSQL, on the other hand, is all about performance. So you design the schema per the queries that you want to do. And this means that you have explicit control about how they're going to be executed and usually how long it's going to take, because you can guarantee that the queries are not going to be executed in an overly complicated way. This also means that queries are much, much simpler. You can't do arbitrary complex queries in a database like Scylla. This also means that you duplicate data because you're going to store it in multiple shapes if you have multiple queries, because as we mentioned before, you basically shape the data in advance when you write it. So this also means that you have to separate the reads from the writes because you're doing shaping on the right side. So often you see architectures that are like CQRS, where command query responsibility segregation, where you have this separation between the read path and the write path. So how does that look in terms of performance? What's the difference? In performance, we're talking about queries that are basically, they have the same semantics. So we took YCSB, which is an industry standard benchmark for databases from Yahoo. and that everybody uses, and we ran it on Scylla and CockroachDB. We just selected one of the popular NoSQL databases out there. And we actually wanted to run both of them on the same amount of data, same data set, but we couldn't because Cockroach couldn't handle 1 billion rows. So we ended up running CockroachDB on 100 million rows, and Scylla we ran on 1 billion rows as we planned because there were no problems. And so this is workload A. Workload A consists of 50% reads and 50% updates. So it has a high contention because it's basically reading and writing from the same rows. And as you can see, the throughput is about 10 times higher for Scylla, although it's actually, it has a data set that's 10 times bigger. And also the latency, even on the high percentiles, is much, much lower. And this is basically the difference that you get when you don't have to do all those transactional semantics. You get a lot back in terms of performance. This is workload D. So 95% reads, 5% inserts. This is something that has no contention because all of the inserts are new rows, so they're not touching the same rows. So you would expect that in this case, relational database won't have as many issues because there are no data dependencies at all. But even in this case, the throughput is like much, much higher. And as you can see, the difference in latency is insane. And this is a more interesting workload. This is workload F, which is pseudo-transactional. You do read, modify, write. So you read a value from the database and you modify it and you write it back. And as you can see, again, there's a big difference in throughput and also in latency. So the interesting thing here is that the tail latency, like the P99, is very big. And this is what happens when you have a lock. When you have locks, because locks often have the greatest impact on the tail latency, which is one of the reasons a lot of people want to avoid them. So why is this happening? The reason this is happening is because, as I've mentioned, NoSQL is designed for simple and fast queries. And by the way, if I haven't mentioned this, we published all of those benchmarks on our websites. So if you want to look at the entire report. So NoSQL is designed for simple and fast queries. So obviously, it's going to shine in a benchmark like this. But it goes to show you that maintaining consistency and isolation is very, very expensive. And even if you're not actually using transactions, the fact that you still have to guarantee the transactional envelope and the guarantees means that you're going to pay either way. And it also means that contention is very expensive because you're going to end up, queuing on locks. And remember, the queries can be complicated. So you're going through a query processor, which has to, understand data dependencies and analyze the query, even if there are no data dependencies. So you're paying in CPU and RAM and all of that. And basically, to sum it up, transactional semantics are expensive, and even if you're not actually using, transactions. So we're going to stop for another poll and ask you about your data sets.
Yeah, when people talk about big data, everybody's got a different definition of that. And we want to find out what your definition of big data is. What kind of data size are you using? And this is in your transactional operational database. We're not talking about your data lake, your data warehouse. We're talking about in your operational database. So if you can take a second and answer this poll, that'd be great. It would help us understand who our user base is. So thank you very much for your input. And we'll be moving on.
Thank you. So in terms of performance, there's a big difference in what resources both types of databases use. So NewSQL and relational databases in general, they basically use a lot of CPU because they have to compute the results from storage. Remember, they have to do the shaping on the fly when they execute the query. So they have to do a lot of computations and assembling, and sometimes they have to apply functions, stuff like that, and all that takes CPU. And they have to do this again and again and again because the ability to cache inside the database is limited because you have data mutations and concurrency guarantees that you have to maintain. And when you're writing, you also have to write to indexes and cascading updates and stuff like that, which also means computations and multiple writes and stuff like that, and verify constraints, and of course do transaction accounting. So you end up crunching a lot of CPU and also being lock-bound, meaning that you're limited. Sometimes the CPU just sits idle because you're waiting on lock. So, but this is basically what limits you. Whereas NoSQL is very CPU efficient mostly. So it actually uses the disk a lot more than NewSQL. Why? Because remember, you are actually holding pre-computed shapes for every query that you want to serve. So you're going to have multiple copies of everything. And that's fine because disk is cheap now. So you're going to use disk a lot more. You're going to have much more copies of the data in different shapes. And you're also going to have multiple replicas that you can service from. So that helps with availability and also with performance, but it ends up with you being mostly disk bound. Of course, now with NVMe disks that are so fast, we can actually be also CPU bound because disks have gotten so fast, but in general, NoSQL crunches the disk a lot more. So this brings me to talk about how hardware has changed in the last 20 years. Remember when we moved from relational databases to NoSQL and NewSQL, we're talking about completely different hardware, completely different operating environment. Everyone's running on the cloud today, and even if you're running on on-premise databases, they're like heavily automated now and have a lot more networking and stuff like that. So it's interesting to see what happened in the last 20 years in terms of hardware. So this is a graph of RAM prices, and I actually have data all the way from the 50s. But if I showed you the data from the 50s, you wouldn't even see this part because it's exponentially dropping. So this would look like a tiny line that is close to zero. And you can magnify it as much as you want. It's still going to look exponential. And as you can see, the prices are dropping like insanely. And also, if you looked at the graph of the RAM size, then it's also exponentially growing. This is a more interesting graph. This is a graph of CPU data from the last 40 years or so. And this is a log scale graph. The y-axis is on log scale. And that means that the red dots that have like a linear shape, it's actually exponentially growing because it's log linear. And this is the graph of the number of transistors. So this is known as Moore's law, meaning that the number of transistors is being doubled every year and a half or so. And this is still true today, although those talk about Moore's law come to an end. And this is interesting because the single thread performance, which is the blue dots, is actually plateauing. So we're not getting faster CPUs. This has been true since in the last decade or so, and definitely since 2014, because we can't make CPUs faster. If you look at the frequency graph, which is the green dots, we reached to the point where if we make the CPUs run at a higher clock rate, the silicon would melt. This is around 5 gigahertz, and we're actually running most of the CPUs around 2.5 or 2 gigahertz for the reasons of power efficiency. We don't want to waste too much power, so we can't get faster CPUs, and that's a big problem. What do we do instead? If you look at the final line, the black dots, you look and you see that we have an increase in the number of cores. So this is how we scale CPUs now. The reason we have more transistors, although CPUs are not getting any faster, is that we're getting more and more and more cores. So to summarize the changes, we're getting more cores, but every core doesn't get faster. And actually, if you look at your laptop, the CPU in your laptop is probably roughly the same speed, or at least order of magnitude same speed as the CPU that you had 5, 6, or even 8 years ago. But the number of cores is inflated. So if 20 years ago we had 1 core on a server or 2 cores, now we have some servers with 256 cores and even more. In terms of RAM, the size of RAM grew by a factor of 1,000 from gigabytes to terabytes. And similarly, in disk space, we grew from disks of 10 gigabytes to 10 terabytes. This is like the largest disk that is sold commercially today. And next year, we're probably going to see 20 gigabytes, terabytes even. And disk sync time at the same time has been reduced by a factor of 1,000 from the milliseconds range to the microseconds range. And this happened because we moved from magnetic disks to SSD and then finally to NVMe. So we have disks that have insane latency now. And in terms of network, the network latency hasn't changed much, but the throughput has grown by a factor of about 100, and it's still growing. So we're going to see 200 gigabits and probably 400 gigabits very soon. So the largest machine you can get on Amazon right now is the U24 TB1 metal, which has 224 cores, which is like 448 hyperthreads, and has 24 terabytes of RAM. This is not the largest machine you can get if you're buying physical machines. You can get bigger commodity machines than that. And of course, on Amazon, you can get much larger machine and much smaller machines. So it's not a problem to get like machines with 2 terabytes of RAM or 6 terabytes of RAM or 4 terabytes of RAM. So actually a lot of data sets that were considered huge back then, they actually fit in RAM now. So the problem is that if we have all of those cores and RAM and disks and machines, like how can we use them? Because the software that we have, and remember a lot of the databases I mentioned that MySQL and Postgre are from the 90s. So like we have software that's 30 years old, it wasn't designed to run on those kind of machines. So how can we use all of those cores? So this brings me to speak about how we scale things in general in software engineering. And we have three major strategies for making things scale. One is to use larger and faster hardware, and we kind of exhausted that because we can cram more cores on a single server, but then we have to somehow coordinate between the cores, and it ends up being kind of a distributed system. And all the problems that we have in cluster, we have in small scale, but inside of single server. So we kind of exhausted that option. And remember, cores are not getting any faster. We can replicate the data, which increases throughput, but then we start having all those CAP and Pecalic theorems problems, which means that we have to do a trade-off between latency and consistency and availability and that kind of stuff. So yeah, that's kind of a problem. And we can shard data, meaning that we can split it into parts that don't interact with each other, which increases throughput again, but it limits the data semantics, meaning that if you want to interact between shards, you have a problem, which is why doing joins and transactions between shards is such a big problem. So because every strategy has its own problems, what we do is we combine all of those strategies. And this is basically how we scale things in modern software. And this is the universal scalability law, which is basically a mathematical model for scaling. And it's called universal because it applies to anything, basically. And what the model basically says is that when you are increasing the load or adding more and more resources to a system throughput will start to grow. And initially it will grow linearly, meaning that the more resources you add, like you get more or less equivalent or proportional growth in throughput of the system. But at some point you start getting diminishing returns. And why do you get diminishing returns? So this is known as Amdahl's law, which states that the speed of a system is limited by the serial part, and every system has a parallel part and a serial part. So once you start hitting contention on locks and like single rows or single partitions or any shared resource for that matter, it could be a shared one disk or one CPU, then you have to wait in a queue and you have diminishing returns. Yes, the parallel parts will still provide extra throughput, but you're going to wait on the serial part, and this basically limits the scaling that you can get. So you start getting diminishing returns, and the more you add, the less gains you get. But at some point, you start getting into an area that's known as the coherency area, in which actually you get not only diminishing returns, you actually are going slower. So you add resources and you increase the load in the system, but the system is actually giving you less and less throughput. And why is this happening? Because if all the players in the system, all the entities in the system have to coordinate and they have to wait for each other, then statistically speaking, the more you have, the more they're going to wait. So any consensus system or system that needs synchronization has this problem, and this is why Paxos and Raft and other consensus algorithms don't actually scale beyond like 7 machines or so, because at that point they start to slow down the more machines you add. So that's a real big problem in distributed systems, but generally when we're scaling stuff. So when we're talking about databases, the way to avoid those problems of coherency and contention is to avoid cross-shard and cross-replica interactions. Of course, you can't avoid them, but if you can, so at all costs, and if possible, then we avoid cross-shard and cross-replica interactions, and this is how we scale things. So what happens with transactions? Remember that if you're running a distributed system and it can have arbitrary transactions, that means that you can do transactions between replicas and you can do transactions between shards. And if you do that, then you're going to hit those limits of the USL, the Universal Scalability Theorem. So we try to avoid them if we want to scale. And the thing is that in reality, there are very few cases that actually require atomic transactions. It's sometimes very handy to have them because it's an easy way to solve consistency problems, but you can solve a lot of problems without that. So there's an example that gets thrown a lot that like, how can you do financial transactions? When I say financial transactions, I mean business transactions. How can you do them without ACID guarantees? And the thing is that actually the world banking system predates ACID by a long time. And actually everything in banking is actually not using transactions. And the proof of this is that we have chargebacks. So the financial system actually runs without database transactions at all. And we also have a lot of other examples. So remember that in the end, what we want to solve is business problems. And sometimes it's cheaper to handle, let's say, rejections or reconciliation on the business side. So for example, Booking.com, they decided that it's not worth dealing with this in a database. And what they do instead is they have a special support team that whenever one of their clients gets to a hotel, because this is like the worst case, that a client gets to a hotel and he thinks that he reserved the room, but there's no room for him. This is like the classic, balance less than zero problem. So what they do is they just have a special support team that finds another room for him, possibly a suite, and they give him like a room that's better, and it costs them maybe $1,000 this whole process to a client, but it happens so rarely that it's much cheaper than solving this in database. And Amazon.com, when they moved their e-commerce system from Oracle to different databases, they actually did something similar. So transactions are very, very expensive. And sometimes they're impractical because if you're trying to do them on a global scale, for example, then often it's impractical for speed of light reasons and availability reasons, stuff like that. And also because sometimes you have logical reasons why you can't do this. And what you can do instead is use immutable data models with reconciliation. And that's almost always better if you can do this. Sometimes you have to do this because of various laws or various regulations. For example, banks have to keep ledgers, which is basically an immutable log of everything that happens. Because remember, database failure and programming failures are not the only problems that you can have. You can have business problems, you can have human problems, you can have disasters, you can have bugs in the code. So you actually, in a lot of cases, have to keep ledgers and immutable data anyway to deal with problems outside of the database. And if you are already doing this, then you might want to use that to avoid transactions if possible. And the thing to remember when you're thinking about database transactions is that actually you're not trying to solve an ACID model or a data model. You're actually trying to solve a business model. And the business model can fail, can have different failures, and you have to think about the recovery of those business failures, just as you need to think about the possibility of having a database abort, a database transaction abort, because every time you're running a transaction, it can potentially abort for various reasons. The database can decide to abort it, or you can have a network failure or whatever. So we have to deal with those anyway. And if you can deal with possible database failure when you're dealing with business rejections of whatever kind, then sometimes it's better to do this. That said, database transactions do provide convenient and familiar model to handle data consistency, and they're very, very beneficial in terms of making your code simpler in a lot of cases. But of course, the world itself is not globally consistent. and often you can't do this. So the canonical example of this is, the social media systems that we use every day, or things like Google search engine. None of that stuff is consistent. If I send a message on Twitter, then my friend who's sitting next to me is going to see it at some unknown time, and it's possible that you will see the message and then it's going to disappear and come back afterwards, and it doesn't matter. The business kind of works because the business implications in those specific systems are not that bad. So it ends up being kind of a business-specific thing, whether you want transactions or not, or the level of consistency that you need. And not only that, it changes even inside one system. So for example, when I was building e-commerce systems, we needed transactions for stuff like inventory or payments, but for a lot of other things like shopping carts and personalization, stuff like that, we didn't need transactions. So we didn't use like a relation database because why? It's a lot easier to scale other stuff. So to summarize the differences between NoSQL and NewSQL, you can put that on basically, if one take one dimension, you can put it on a spectrum from query power and data integrity. This is where NewSQL shines, to the other side, which is like performance and scale, and this is where NoSQL shines. And the difference in terms of how you program is that in NewSQL and relational databases in general, you're going to have code that's much more centric to the database. You're going to write around the database, and all of your data mutations, data handling code is going to be basically running inside of the database. Whereas in NoSQL, you're going to do all of that inside of your application, which means that you have more control, but also that you're going to have to write all that code inside of your application and deal with it. So NewSQL means generic data model, ad hoc queries and all that. It gives you strong consistency, database transactions, but limited scalability, and it's slower. Whereas NoSQL has a query-specific data model. You have to model per the queries that you're going to have. It has tunable or weak consistency, no transactions, but it's very scalable and very, very fast. So thank you very much. And if you have any questions, now is a good time.
All right, we actually do have a couple of questions. Darshan asked, if a company decides to move from RDBMS to NoSQL, is it feasible? And what are all the variables and constraints that need to be considered for the migration?
So that's an excellent question, but also a very complicated question. So first of all,
exactly.
there have been quite a bit of large-scale migrations. I think the most famous one is the migration that Amazon.com did on 2018 from Oracle to various databases. They actually moved a lot of those stuff to DynamoDB, which is also a NoSQL White Rose database. Some of those stuff they moved to Aurora, the stuff that needed to be in a relational database, but most of the stuff they moved to NoSQL. And there's actually, they published quite a bit of material, some lectures and some write-ups about this, and I highly recommend that you go and look for it. But the really important thing there is to understand, per business application that you're moving, what are the specific constraints and what are the specific needs for that application, and then you can understand like how you solve it and how much you can relax your consistency guarantees. That's like the main thing. Peter?
Okay, yeah. I'm going to provide a link to another webinar we actually did on that migration. Here's another question we had then from Franklin. NoSQL has storage affinity as opposed to CPUs. So should we strive for sequential access instead of random access? And what's the impact of tiered storage due to data explosion?
So that's also another very interesting question. So first of all, it depends on the database. So not all NoSQL databases have this storage affinity that you're talking about. So Scylla, for example, allows you to decide that you want to host a bunch of data in one partition, and then that data is going to sit together inside a partition. But you can also distribute the data such that every datum is on a different partition, and then you can do random access, but you're not going to be able to do scans, so it's kind of a trade-off. But in general, NoSQL databases, specifically Scylla, are so good at giving you high throughput that often you don't have to specifically designed for sequential access. It does help if you need to read in a single query a lot of data. So it basically depends on the queries that you're making. In terms of tiered storage, yes, that's usually a good idea. Why? Because first of all, we try not to delete data if possible, and we try to preserve, historical data and stuff like that, whether it's for machine learning purposes or backups or recovery or whatnot. And of course, we have very cheap storage that has, of course, higher latency and lower throughput and so on. So it makes sense to use it and save on costs if you don't need it. And but again, this relates to specific business case. So in some cases it doesn't make sense. In some cases it makes sense, and there's like a lot of trade-offs in that.
Right. We had another question from Rambabu about how different is Scylla from the Microsoft Cosmos DB. I will say that before we get into the comparison, we do not have a benchmark, but we do have benchmarks against DynamoDB and Bigtable. But Avishai, would you like to talk about the comparison between those two?
Yeah. So they're actually very, very different in terms of how they're built, but they are similar in some of the, let's say, in the APIs. So both of them provide CQL APIs. You can actually use CQL driver with both of them and seamlessly move between them, but they're very different in terms of what they offer in terms of operationally, of course, because Scylla, for example, can be hosted. You can host it yourself, whereas Cosmos is only offered as a software as a service. You cannot host it yourself, which means that if you're on-prem, it's not available. If you're moving to a different cloud, it's also not available. So that's one big difference. Second difference is in terms of latency. The latency that you're going to get from Scylla is a lot better. That's part of the trade-off, I guess. But also in terms of features, there are some features that we provide that they don't provide, and there are some features that Cosmos provide that we don't provide. For example, they support APIs that we don't, and so on, so on, so on. So there are differences, and architecturally speaking, it's like built in a totally different way. Like, yes, there are some architecture and decisions that are similar, like sharding and partitioning, but otherwise it's very different.
Okay, thanks very much. We actually have a number of additional questions. And I would implore anybody that's got a burning question to join our Scylla user Slack. I want to thank Avishai for his insights today. I want to thank all of our attendees. We look forward to you attending our next webinars. Thank you.
Thank you.